We didn't get a chance to get very far into Chapter 9, Tap 4 today in class, so I am putting a screencast up. Anyway, this is the answer. I have the blank taps for Chapter 9 up at the Moodle site. I also have answer keys. I'd recommend trying to struggle with the blanks before you look at the answer keys, but that's up to you. All right, let's dive into this one. Given market prices, how many pails of water will each child fetch from the top of the hill? Well, there we're just going to apply the cost-benefit rule. And each pail is worth $5. Would you bring the first one down the hill? And these kids are acting individually. Well, take it from Jill's perspective. It costs her $2 worth of effort to bring the first pail down. Get $5 for it. You bet. Given that she's bringing one down, would she bring a second one down? This is this funny way we set up microeconomic problems. Well, given that she's it costs her $3 to get that second one, $3 worth of effort to get that second one down the hill, and she gets $5 for it. Well, $5 is bigger than 3. She'll bring it down. That first part, there's not a whole lot interesting going on there, but it sets us up for the next part. So 2 is the answer, and it's true for Jill. It's true for Jack. All right, let's think about this socialistic system that Jill and Jack's parents impose on them and how that changes the game. All right, now when their costs of effort are still the same, the price of a pail of water is still the same, but now they have to split whatever revenues, and this creates a game that this problem asks us to think through. So if they each bring down 0, let's fill out this payoff matrix. If they each bring down 0, they get 0, they spend 0 worth of effort, Jill gets 0, Jack gets 0. But let's say Jack brings down 1 and Jill brings down 0. Well, so there's 1 pail of water. Jack has carried down 1 pail, but he's got half the revenues. $5 divided by 2 is $2.50. But he's also had to expend $2 worth of effort. So his net is 50 cents, $0.5. Jill, on the other hand, doesn't have to expend any effort, and she gets half the revenues, $2.50. So that's the payoff to her of staying down at the bottom of the hill and watching Jack work. Well, it's a symmetric game, so if Jill's the one carrying and Jack's the one watching, the situation is reversed. Jill ends up with just 50 cents net, and Jack's the one with $2.50. And we'll just go through this payoff matrix with this in mind, and then we'll solve for the equilibrium, that if we do our payoff rights, the equilibrium won't be too bad. All right, well, let's think if Jack carries 2 pails down and Jill carries 0. Now there's $10 total revenue, 2 times 5, split evenly. They each get 5. Jill hasn't had to do any work, so that's easy. But Jack has carried the first one down and the second one. $2 worth of effort for the first one, $3 for the next one. He nets 0. His revenues are 0, and his revenues are 5, and his costs are 5. So 5 minus 5 is 0. All right. Well, it's symmetric, so we can know that the bottom left payoff is just the flipped, the reverse of this top right. All right. Let's look where they each bring down 1, and then. Now we've got 2 pails of water, and that brings in $10 worth of revenue, and they each have spent $2 worth of effort bringing that pail down. So their share of the revenues is 5, their effort is 2 each, so they each get 3. And then there's no flipping that one over. Let's do where the case where they each bring down. No. Let's do the case where Jack brings down 2 and Jill brings down 1. Now their revenues are $7.50 each, right? 3 pails of water. Jack brought 2, Jill brought 1. So $15 divided by 2, they get $7.50 each. Now Jack had to spend $5 worth of effort, so he clears just $2.50. Jill spent just $2 worth of effort, so her net is actually $550. She got $750 in revenues and only spent $2 worth of effort. Well, it's symmetric, so if the shoe is on the other foot, the pail is in the other hand, whatever, then it's going to be flipped around. And then finally, if they both carry 2, the revenues, there's 4 pail of water total. That's $20 divided by 2. That's 10 last time I checked. They've each spent 5 worth of effort. They each clear 5. All right, so what's the equilibrium outcome? Let's think about this. You might be tempted to jump to the notion, oh, they'll each carry 2 down because that's the highest payoffs, but that's not the dynamic of this game. This is a prisoner's dilemma game as it happens, but let's just see how that works out. I'm going to change my pen color to solve for the equilibrium. Let's go orange just for something different. All right, let's think it through from Jill's perspective. If Jill thinks that Jack is going to carry down 0 pails, she's going to examine all these payoffs and decide what she's going to do. So if she thinks Jack is going to carry down 0, she could carry 0 and get 0. She could carry 1 and get 50, carry 2 and get 0. So she's going to carry 1 pail if she thinks Jack is going to carry 0. Let's suppose she thinks Jack is going to carry 1 pail. She could carry nothing and get 250. She could carry 1 and get 3. She could carry 2 and get 250. Well, 3 is bigger than 250, so she's also going to carry 1 pail if she thinks Jack is going to carry 1 pail. Well, what is she going to do if she thinks Jack is going to carry 2 pails down? She'd carry 0 and get 5, 1 and get 550, or 2 and get 5. Well, lo and behold, she'd also choose to carry just 1 pail down. It turns out Jill has a dominant strategy to carry 1 pail down, and it's a symmetric game, so Jack has a dominant strategy to carry 1 pail down. Well, as in any prisoner's dilemma, there's one Nash equilibrium, and it's where both parties play their dominant strategies, and that's going to result in each carries 1 pail. Payoffs are Jill gets 3, Jack gets 3. And notice that this is our usual prisoner's dilemma result. There is a better outcome, this 5-5 if they each carry 2, but this notion their parents had of having them share equally create this game where they each end up with this dominant strategy to just carry 1 down. And that's how you solve this game.